Okay, gang, let's begin. We talked about Archimedes' principle. True or false? True or false? Archimedes' principle says that the amount of buoyant force that's going to act on any immersed object will be numerically equal to the weight of the object.
False.
False. Let me try another one. Very good. Archimedes' principle says the amount of buoyant force that will act on an immersed object is numerically equal to the weight of the fluid displaced by that object. Sure. Hey, huh? There's a difference, right? Is that true? Let me ask you a question like this. Here's a piece of iron. Very, very dense. I'm going to put the iron in the water. Yucko! It sinks. Boom! Really sinks. Some people say, well, that's because there is no buoyant force acting on it. And you say, there is or isn't? Answer begins with an I. Is. Okay, you like that hint? Okay. Turns out there is. How about this piece of wood? This piece of wood have the same size, has the same volume. I'm going to put that in. People say, oh, there's a buoyant force acting on the wood. Some people would say the fact that the iron sinks and the wood floats is evidence that there's more buoyant force on the wood. To that, you would agree or you would disagree. Knowing they're the same volume, see what your neighbor says. Which has the greater buoyant force, the sunk iron or the floating wood? And realize they're both the same size, same volume. How many say there was a buoyant force on each, and son of a gun, the buoyant force was greater on the submerged iron? Some people say that, but some people don't. Now, let's use Archimedes' principle to answer the question. Archimedes' principle says the more water displaced, the more buoyant force. Yeah or no? Yeah. So if something displaces a lot of water, a lot of buoyant force? How about something displaces only a little bit of water? A little buoyant force. Okay, these both get the same volume, same size. When I put them in, one sinks. Now, I'm going to ask you a question. Which has the greater buoyant force? And when I ask that question, I want you to use Archimedes' principle to answer the question. Let's suppose instead I said, which one displaces the most water? The one that sinks all the way underneath, or the one only sinks a little bit? What would you say? This side of the class. What would you say? The one that sinks all the way? The one that sinks all the way happened to be iron. And the one that sinks all the way displaced the most water. So the one that sinks all the way has the greater buoyant force. Do we all see that? So one is floating and one's sinking. There's two things to consider, gang. Two things to consider. Here's my object in the water. Here's the buoyant force. But there's something else to consider. Here's the weight. In fact, it's a lot more than that. Turns out the weight will be over 5 times as heavy as the buoyant force for iron. Iron's very, very compact. Iron's very dense. Nevertheless, there's the buoyant force. If I took this iron and held it like this, which has got the greater buoyant force? The iron like this or like this? Or like this? Yeah. See, so the buoyant force has to do with the weight of water displaced. And it's going to displace a lot more water like that than, say, if it's up here floating. I don't have to tell you if this is wood or iron. All I have to tell you is, hey, how much water is displaced? You got the answer to how much buoyant force. So the thing that has the greatest buoyant force is the thing that displaces the most water. Do you kind of see that? Okay. Here's a piece of clay. We talked about this last time. Here's a hunk of clay. Take the clay. It sinks. Any buoyant force acting in the clay? Yeah, there's a buoyant force acting in the clay. How much compared to the weight? There must be less. The weight must win. That's why it's on the bottom. So the weight wins. What I'm going to do is I'm going to refashion the clay and make it into like a boat. Now when I put it in, it will displace more water before it sinks. And let's see if it displaces enough to... The same clay floats. HC. How many say? I don't know. I didn't be knowing clay floats, but some clay floats, honey, if it got the right shape. Or is there more to it than that? Is there more to it than that? When I made the clay wider, didn't it displace more water? Guess how much water it has to displace to float? As much as its own weight. Because now, guess how the buoyant force compares to the weight? One guess when you see the system in equilibrium, not accelerating. Take a guess. Don't even take a guess. Take an estimate. What is it? And you know what it is. The same. And that's a complication for a lot of people, because for floating objects, the buoyant force not only equals the weight of water displaced, it also equals the weight of the object doing the displacing. Can you see why some people, boom, they can't handle it? They get mixed up. So it's only when you float that the buoyant force and the weight of the object are both the same. See? If I make the buoyant force less by having it displace less water, then the buoyant force is not big enough to support the weight, and so the weight's the same, buoyant force is less, and it goes in the direction of the net force. Yeah? Kind of see that? Make sense? Wait, question?
When you reshape it, though, you aren't changing the density of the clay by itself. So what makes it less dense overall?
Yeah, we haven't really talked about density yet, have we? But it turns out I don't change the density of the clay. But I do, nevertheless, when it's submerged like that, get a big air pocket. So as far as the water is concerned, there's something with something of less density when you consider the space that the air pocket takes up. So counting that's like a hollow piece of iron, of course, will float, see? Because it's got the air inside. So the overall density is less. So I could say the overall effective density, if you count from, counting the air that's trapped in there. Not trapped in there, but which is supported. Kind of something like that. Let's talk about density. Make that a little clearer, I hope. There's an object. I'm not going to tell you what the object is, because we don't care what the object is. That object in there is taking up that much water. We say it's displacing that much water. Hey gang, if you weighed that much water, you got a value for it, okay? How would that compare to the buoyant force that acts on that unknown object? Begin with SS. Same, okay? In fact, the weight of water displaced is going to give me an upward buoyant force. Now let's suppose this object happens to be a baggie filled with water. Then how heavy will it be? And turns out it'll be just as heavy as the buoyant force. So you know what it does? It doesn't sink, it doesn't float, it just remains at one with the water. Because it has the same mass as the same volume of water, which is to say it has the same density. So if something has the same density as water, it's not going to float, it's not going to sink, it's going to do neither. The density of water is 1 gram per cc. 1 gram per cc, or 1 kilogram per liter, or 62.4 pounds per cubic foot. That's the density of fresh water. I got a question for you. Is there anyone in here that happens to know the numerical value of density for a freshwater fish? Check your neighbor. Any buoyant force in a fish, gang? Show me a fish with no buoyant force and I'll show you a fish in a vacuum. Okay? A fish is displacing fluid, usually water if it's healthy, right? And so there's a buoyant force acting upward. Any gravity pulling on that fish? Oh yeah, and that's pulling down. Guess how hard the gravity is compared to the buoyant force that's such that the fish stays there? Come on. Same. So what's the density of the fish?
1.
The same as water. So if I tell you water has a density of 62.4 pounds per cubic foot, then you guys know what a fish density is in cubic feet. 62.4 pounds. Okay? Guess what your density is? More or less than 62.4 pounds per cubic foot? More or less?
Less.
All the ladies in the class be saying less. Most of the dudes be saying less. But some dudes say, hey honey, you ain't talking to me because I don't know why. But I try, and I just can't float. And my friends are telling me why, and they're all saying that I'm too... yeah, too dense, yeah. People that have no fat, very, very muscular, very compact, are a little bit more dense than water. They sink in water. See that? Because let's look at this over here. This is the size of anything. If the weight is like that, then it weighs more than an equal volume of water. What can we say about its density? Greater than an equal volume, greater than water, that of water. What's this object with the net force is which way? Down. Which way is it going to go? Down. It's going to sink. So objects that are more dense than water will sink in water. And we see why. Because the buoyant force is not enough to keep up with the weight. Let's suppose this object has a weight like this. Very small compared to water. Okay. Any buoyant force? Yeah. Buoyant force the same as before. Remember, the buoyant force doesn't have to do with the weight of this at all. It has to do with the size of it, how much water it's taken up. It has to do with the weight of water displaced. And that depends on the size of the object displaced in the water, yeah? This object here now has a net force acting which way? Begin with a U. End with a P. Put it together. Up, okay? Guess which way it goes? It goes up until it floats. See? It'll finally go to the surface and get to a point here. Now, there's less buoyant force at the surface. Is there less buoyant force at the surface? Yes. You bet there is, okay? And now that weight and that buoyant force both balance and it floats. So here we have the idea that the weight of the object itself equals the buoyant force. And that's the principle of flotation. So if something's more dense than water, it sinks in water. Less dense, floats in water. Same density, stay right there. I got a question for you. Here's our fish. It's in a bowl. It's our pet fish. We like that fish. We find out that when we feed that fish, the fish goes right to the food. If we put the food in the bottom, the fish goes down and gets it. Put the food in the top, the fish goes up. How does the fish go up and down? It takes its flippers and goes down like this and then goes back up like this, right? Let's suppose we take those flippers and cut them off. It's for science. All right. Now we can take the tail and do it, right? All right, we cut the tail off. Okay. Now, let's suppose that's a little cruel. Let's suppose we just take the flippers and put Scotch tape over them, okay? And put a couple of splints in the tail. Okay. Now, how can the fish go down if it wants to go down? How many say, it can't do anything now, get no flippers? How many say, I think the fish still can go down? Here's our little hint. If the fish is going to go down, what does the fish have to do to its density? Make it more or less? Is there any way for the fish to change its density? Yeah. What can it do?
It off the air.
It can contract its pure bladder.
It can make its volume smaller. If it pulls in on its bladder, it will sink, okay? And so let's suppose all of a sudden you put better food at the top. How's it going to get to the top? It's going to push out, make the volume larger, and it's going to go right to the top. So a fish varies its density by varying its volume. Submarines, crash dive. They're down there, they come back. How does a submarine do that? By varying its volume? How does a submarine dive? How many say this? How many say, hey, I learned enough physics that I know this, that if a submarine on the surface dives, then I know that submarine must have somehow become more dense. How many say, I don't see the connection? You're swimming and someone hands you a boulder. Guess what you do, honey? Okay? Your overall density becomes more, and what do? Begin with an S. You sink. And so the submarine becomes more dense, not by changing its volume, but by doing what? There's only one other choice for density. The equation guides our thinking, doesn't it? If it's not volume, what's the other choice? Weight. And so the submarine gets heavier. How does it get heavier? What's it do? It drinks water. Water's heavy? If you have enough of it, yeah? And that water drinks water, becomes heavy, and just sinks. Now it's down below. Hey, we want to come to the top. What do? Blow the water out. So the water's out, the submarine becomes lighter, less mass, right back up again. So a submarine does it by changing the weight, and fish do it by changing the volume. Got a project for you for Saturday night. Saturday night when you take your bath, okay? Get everyone else out of the tub and bathe alone, okay? Parents say anything, say, hey, this is for science, I got the bathtub all to myself tonight, all right? And here's what I want you to do in that bathtub. I want you to float back in the tub, and I want you to take a great, big, deep breath. And when you do that, see if you don't rise right off the tub. And when you're floating really high, then I want you to blow it all out and boom, boom, boom. See if you don't crunch right back down on the bottom. What's going on there? Have you guys tried that? Yeah. You take a deep breath, you rise in the water, let it out, and you go down. HC. Submarine or a fish, like a fish. See? When you take a breath, don't your lungs get bigger? Your volume gets larger? Okay? So you don't have to sink as deep to displace the same amount of water. So you'll float higher. So when you're high, then you go, like that, what happens? You cave in, you become more dense, and you sink. When you're floating, some people, you're trying to teach your friends how to float, and they're kind of freaking out, kind of. You tell them, hey, take the deepest breath you can. Now hold it. Are they going to float easier? Yeah, they're going to float easier because what's happening? Their volume is increased. And so long as you keep as much air as you can, it's not the air, it's the idea that your lungs are out, see? And if your lungs are out, you're less voluminous, more voluminous, and you'll float higher. Or how about you just barely can float and you let it all out. Okay? I tried something yesterday in a swimming pool with a snorkel. I wanted to see how deep I could go with a snorkel. It turns out I could go about 30 inches, less than a meter deep. Because when I get down a meter deep, and I'm trying to breathe with that snorkel, I put a piece of plastic tube in the end of the snorkel. When I get down there, I can just barely breathe. HC. The pressure of the water, honey, was pushing me in and contracting me and making the pressure in my lungs more. It turns out the pressure in your lungs will be the same as the water pressure outside. It'll squeeze in until it is. And now I've got more pressure 30 inches under the water, more air pressure in my lungs than up there. How many people say, oh, just go like this, and all the air will rush down. It's not going to go from low pressure to high pressure. When I was a kid, I used to think that if you were a deep sea diver type, all you'd have to do is take a garden hose, put it between your teeth, and swim down. And you breathe it off the top. But I forgot about the idea that the water pressure squashes you in. And it's going to, any air you got in there, honey, go this way. Could you imagine going down quite a few feet? You got your lungs full of air. Someone hands you an empty hose. What you got's going to, you'll get even, hey. You see that? Water pressure depends on depth. Let's put all these ideas together and see if we can handle this one. It's life preserver time. And you look over there and you see two life preservers. And they look both to be the same. Nice orange color of the tags and everything. Except one is filled with styrofoam and one's filled with lead pellets. Someone says to you, if you use the one with the lead pellets and they're both the same size. This is critical thinking time, gang. Someone says to you, if you put on the life vest filled with lead pellets, turns out you'll have more buoyant force on you than if you use the one with the styrofoam. And someone says, you know what? That guy is right. There will be more force, buoyant force, acting on you with the lead pellet one. Yes or no?
Yes. Yes.
That's like saying this. Hey, you want to be held up? You want to grab one of these? Well, I tell you what, if you grab the iron, there'll be more buoyant force on it than if you grab the wood. What's the answer? Yes. There's only one trouble. You're not interested in only the buoyant force. You're interested in something else. The net force. And gang, the weight is going to overwhelm that greater buoyant force. It turns out the lead pellet-filled styrofoam life vest will give you more buoyant force because why? Because it'll sink beneath the surface and displace all of its volume. Whereas the styrofoam one will be up like this, eh? This part here you're not even displacing. So when you put on a life vest, all you're doing, gang, is you're decreasing your overall density. And when you increase your overall density, you do that by increasing two other things. One that you want to increase and the other that you don't want to increase. And the one that you want to increase is what? You want to increase the volume, so you get the puffiest thing you can. Now that puffy thing is going to have some weight, right? But not very much compared to the volume, and so even a small life preserver will float you nicely. All it does is it adds to your volume while only adding a little bit to the weight. So the friend that hands you the lead pellet one, sure, they add even more to your volume, but humongously more to the weight, and that's why you drown. So strictly speaking, we see that there's a difference between the buoyant force that acts on something and the net force that acts on something. Would you like another critical thinking type question? How many say, no, I'm tired, that's enough? Let's try this one. Some years ago, I had the good pleasure of swimming in the Great Salt Lake in Utah before it became inundated with fresh water. It used to be very, very salty and very, very dense. And you could float in the Great Salt Lake. Honey, you're up like this. Or like regular water, you're down like this or something like that. Or kerosene, you'd sink, okay? Not too much density. Okay, but in that Great Salt Lake, you could float very, very high on the water. Now, that's because there's more buoyant force on you if you float in the Great Salt Lake.
No.
True? False? I don't know, who knows? Check the neighbor.
The right answer is
Okay, gang, what'd be the answer? How many say, no, it turns out if you float in the Great Salt Lake, very, very dense water, but you know what? The buoyant force is going to be just the same if you float in there as if you float in the ocean. Same buoyant force. How many say, yes, that's true? Hands. How many say that's not true? Hands. Maybe I'll leave that one for you to think about. But I could give you some hints. And I could say, do you float in both cases? Isn't there a little rule for floating? When something floats, the buoyant force will be how great? Equal to what? The weight. So when you float in the Great Salt Lake, what's the buoyant? Let's suppose you're a 120-pounder. What's the buoyant force on you? 120 pounds. Let's suppose you float in the lake, freshwater, and you float. What's the buoyant force acting on if you're a 120-pounder? 120 pounds. So the buoyant force is going to be the same in both cases?
Yeah.
Question.
What about because you float higher?
You do float higher.
All right.
You float very high in the Great Salt Lake.
So wouldn't that...
Wouldn't you displace less water?
Yeah.
You would displace very, very much less water. Less volume of water. Can we start to pull it together, gang? Can we pull these ideas together? You displace less volume of water, but salt lake water, honey, you don't have to have very much of it before it weighs the same as that which you would displace in a freshwater lake. You see the difference, gang? We're thinking carefully about these ideas. How much weight of water you displace and how much volume of water you displace are two different ideas. And for the same weight and different densities, you'd have different volumes.
In the clay boat,
Yeah.
you made it big like that, it displaced more water.
It displaced more water. And when I made the clay boat big, it displaced more water. And what happened to the buoyant force when I displaced more water? Begin with an M. More. See? Enough to make it float.
Okay, if you made it even flatter, would it displace even more
I could make
water?
it so more of it would stick up above the top. I could do that,
So
yeah.
the weight is the same.
The weight's going to stay the same. That's right. But the volume I can change. The volume that the water sees. Now it's floating even higher. Lee?
Suppose that it tilted too much and the water got let into the air pocket inside.
Ah,
What happened?
then the weight is going to increase. Let's suppose there's a leak in the boat, huh? Something like this. Let's try this with a little hole there, okay? Watch what happens now, gang. Oh, it floats. It's very, very wonderful. But all of a sudden, it's getting heavier and heavier, and yucko, 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 okay? Now, the buoyant force wasn't enough to take care of that added weight. That's why when a boat springs a leak, it gets heavier. Gets heavier, and the buoyant force no longer may be enough to make it float. Lee, question.
When you dropped those balls into the water a couple of weeks ago, or a couple of sessions ago,
Yes.
was there a buoyant force on the balls?
Yeah. There's always a buoyant force on anything that displaces water, right? Now, how much buoyant force?
Equal to the volume.
Equal to, well, it really equal to
the weight
the...
of the water displaced by the volume.
That's right. That's right. Yeah.
When you're making the clay bigger, okay, by that equation, wouldn't you be changing its density?
I'm changing. Well,
Because the weight's staying the same, but the volume it's displacing is getting bigger. So the volume of the boat to displace that greater volume of water would have to be bigger. Right?
effectively, the density of that which does the displacing becomes less. The problem is, they say, well, the clay has the same density no matter what you do. That's true. But the volume of clay that displaces the water, that density becomes less because now a lot of it is that air. So in a sense, we're effectively changing the density. The density of a ship is a lot less dense than the density of iron metal because the ship has that open space in the middle. See? So the volume is made bigger by not increasing the weight. If you hold the weight the same, do you see that these equations are nice ways to think about things? See? If you hold the weight the same, but change the volume, then you'll change the density. See, there's all kinds of ideas and considerations to think about with any problem. That's why these relationships at least narrow it down to a couple of things. In this case, to weight and volume.
Okay, let's say you had a ship. Like a home, you have a ship. If we throw a bunch of styrofoam on there, the weight increases.
Ooh,
the volume also
let's
increases,
talk
right?
about that. I left you with
But
a
it's not-
question. I left you with a question, gang. What's going to happen to a ship loaded with styrofoam compared to a ship that's empty? Here's my ship empty. See how it floats? Very high. See this styrofoam? How many say, that ain't styrofoam? Well, I can spread it out and puff it up, and now it is. But it has the same weight, doesn't it? I put the styrofoam in. Oh, that's strange. It sinks lower. Let me ask you a question. If you see a ship loaded with 5 tons of lead, is that going to float lower in the water?
Yeah.
How about you have the same ship loaded with 5 tons of styrofoam crammed in there? Is that going to float lower in the water?
Yeah.
Guess which is heavier, 5 tons of lead or 5 tons of styrofoam? Okay. So they're both going to push the ship down by the same amount. So the answer is, the ship loaded with anything that has any weight is going to float lower than a ship loaded with nothing. Did we kind of get that, gang? Here's the part where people get mixed up. What if you took that styrofoam and you attached it to the outside of the ship? What would happen then?
Higher. Increase the volume.
See, on the outside, you'd increase the volume. Try something like this. Here's a block of wood. It floats that high. What I'm going to do is I'm going to put this piece of metal. Got some elastic bands here. I'm going to put a metal load on the top. And when I do that, is it going to displace more water?
Yeah.
Yeah, it's going to displace more water because it's heavier now. Whoops, still floating. Let's get it so it's a little bit stable. You see how much it's displacing, gang? See where that water line is right to here? I'm going to take this out and turn it upside down. I'm going to turn this upside down. And you're going to estimate where's the water line going to be? Higher, lower, or the same?
Higher.
Lower.
How many say lower? How many say the same? How many say higher? How many say, hey, I'll just take notes, honey? Yeah? Let's take a look at it. It's floating, yeah? Is this a floating object? How much water is going to be displaced by this floating object? Some people say the weight of water displaced is equal to the weight of this. Is it still equal to the weight of this?
Yeah.
Yeah. Look, right there.
All right, but you just increased the volume
Did I?
of the thing, didn't you?
Did I? Did I?
Oh, the wind's sticking out.
Did I increase the volume of water displaced? There's a couple of ways to look at this.
This is tricky.
Now the iron's underneath. It is tricky. It is tricky. It's very, very something to really, really get you thinking, right? Okay. Floats like that. Floats like this. You see, in both cases, it's floating. Notice how far down how far up the water line is on the wood. That's because the whole weight of this is pushing down, yeah? Will this push down as hard when it's submerged? Will it? Won't it be buoyed up itself?
Would be a greater buoyant force on it.
Notice that the wood is a little higher now?
Yeah.
But notice the water level over here is the same. There's a lot to think about there again. A lot. And what I want to do is I want to give you a couple of homework problems, exercises, okay, that will help you to shape up your thinking.
Say that iron thing isn't attached to the wood though, and it's in the water. Will the water rise the same amount?
If it wasn't attached, of course, then it wouldn't interact with the wood. You mean like if it were tied?
No, if it wasn't, if it was just in the water and the wood was in the water, but it's separate.
Well then, I see what you're saying. Okay, like over here. Oh, your question is going to be very helpful to the question I'm going to ask you. So I won't answer you. The role of teachers are not to give answers. The role of teachers are to what? Provoke questions. And who should be the one to remember to find the answer? See, it's thought that when you find the answers to your own questions, that's what you remember. And you might remember when you find the answers to someone else's question, but you'll hardly ever remember the answers that someone else gives to their own questions. So I want to ask you people a question and let you think about it for a couple of days. And here it is. I've got a boat, and the boat is loaded with metal. And look how low it floats. Look where the water line is here, gang. Isn't that something? See the water line? Now what I'm going to do is I'm going to take the metal out. When I take the metal out, what's the water line do? It drops. But now I'm going to throw the metal back in. When I do that, will the water line have a drop, rise, or stay where it was when I started? Like that. That's your question. Here's the water line. When I take the metal out and throw it overboard, overboard, will this water level go up? Will it go down? Or will it stay right there? The thing to think about is now the metal is made to float. When I take it and throw it overboard, then the metal sinks. Any difference in the buoyant force on the metal either way? Something to think about. Question without giving away too much information.
If the water was like all the way to the top and there was an ice cube inside, the ice cube was floating. If the ice cube melt, would the water overflow?
That's a good point. How about that, gang? You've got a glass of water with an ice cube in it. The ice cube sticks up a little bit, yeah? When the ice cube melts, does the water level go higher, lower, or stay the same? I'll be asking you that question at a different time. I got a nice one for you. You want a dandy? This is a dandy. Okay. Here's your question, gang. Consider a balloon floating in the water. The balloon will float like that. It will displace only a tiny bit of water. That tiny bit of water has some weight, yeah? Guess what that weight of water is compared to the weight of the whole balloon? Equal, okay? So balloons float very, very high in the water, yeah? Okay. Let's suppose this balloon, I weight it down. I tie a heavy brass weight on here, okay? And I make it float. I make it so it's just on the verge of sinking. There's my balloon right here. See that? See how that is? I mean, it is, the density of that balloon system, the balloon plus this now must be equal to that of water. Just barely, yeah? I mean, on the verge of sinking, like if I put a nickel or a dime on the top here, I'd increase the weight, and I'd make it sink. But I'm not going to do that. I have it just on the verge of sinking. Now, here's your question. What would happen if I take that balloon and I push it under the water, about a half a meter or so, and take my hand away? When I do that, gang, what happens to the balloon? Will the balloon stay there? Will it sink? Or will it come back up? Ooh. That's your question. That's your question. What will happen to the balloon when you push it under and let go? Will it sink, stay where it is, or come back up? And most important of all, HC. How come? Any questions about anything, gang? Question?
You have to take into consideration water pressure.
Oh, that will very, very much take into consideration water pressure. Very much. And if you don't take that into consideration, then you'll feel yuck yuck next time. How about this, gang? Someone says, oh, the reason wood floats and iron sinks is because iron is heavier. And then you take a paper clip. Glug, 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 glug. Then you take a great big log and it floats. So what's that person mean when he says, oh, that's because the iron's heavier? Denser. Denser. See? Heavy compared to volume, then that's denser. Any other questions? About anything? Okay, we're right on schedule, gang. Next time we're going to be talking about gases. Gases and atmospheric pressure. See you then. Physics. Yay.